Hi guys, Talish here. We've been looking at all sorts of fun encryption things like TLS, certificate authorities, and how they sign certificates. So far, we've been getting our house in order, making sure everything's up to scratch. But today, we start breaking stuff. And by breaking stuff, I mean bending the chain of trust to our will. I know the content has been very generic so far, but don't worry, we're building up to some fun stuff with Magento. So remember, our certificates do two things. Its first task is to always establish an encrypted session between the server and the browser. Its second task, which it has almost universally become known for, is to establish trust via signatures from the certificate authorities. The certificates that we get from these certificate authorities is also called an X.509 certificate. And that name confuses a lot of people trying to figure this out for the first time. Just remember that an X.509 certificate has a much simpler name. It's also known as a domain validated certificate because you find a certificate on a server that wants to validate its domain. As I said, this stuff's rocket science. But what if we want the encryption that these certificates provide, but we don't really need to establish trust because we control both the server and the browser? This is commonly the case during development. We want to test our site with HTTPS enabled because the production site is being served via HTTPS. We know that these signed certificates are not free, and we'll talk about Let's Encrypt on its 90-day free certificates in a future episode. But for testing, we really shouldn't have to go buy a certificate, and even worse, since X.509 certificates are tied to a domain, we really shouldn't have to pay for each test domain. Or even if we're using Let's Encrypt, we shouldn't really have to renew them every 90 days. The simplest way to get around this entire problem is to generate self-signed certificates. There are a ton of sites on the internet that will give you convenient little copy-paste instructions for setting one up. The instructions aren't half bad for a quick certificate. The first one here generates an RSA private key, 2048 bits in length. As I said, not half bad. A 204-bit length is the minimum you should be using. Then it uses that private key to generate a self-signed certificate which will be valid for 10 years. Perfect for testing. I'm okay copy-pasting this into a terminal because, well, I know what these commands do. And actually, even better, I'll make this into a one-liner and drop it into the YouTube description. Just copy that and paste it into your terminal and you should be able to get a certificate in a few seconds. Just make sure if you do so to change the common name or /cn value of the subject to your domain. You'll have a certificate in a matter of seconds, and I'll let you figure out how to install those onto your web server because, everyone uses a different web server. But this is what we get when we try to look at our website signed with a self-signed certificate. And this will show up for every single session. This warning could have been dismissed with a couple clicks in the past, but Chrome and Firefox have changed their user interface, so now the end user has to jump through some more hoops and think a little bit about what they're doing before accepting a self-signed certificate. This is definitely a good thing for the clueless surfers of the World Wide Web. But for those of us who are working on building e-commerce, it quickly becomes an annoyance. Firefox allows you to add an exception so you can keep working. However, Chrome makes you jump through a ton of hoops, and I'm not even going to figure out what IE does. The problem is we want to build and test our sites to work properly with encryption, but we don't want to jump through all these stupid hoops every single time. Even worse, if we have a team of developers and a QA team, doing this every day is just going to make them quit. We just need a way to tell the browser, shut up, we know what we're doing, we're professionals. Luckily, there's a way to do this. And we do it by hijacking the chain of trust and becoming a certificate authority. So we could sign certificates that our team machines trust. To become a certificate authority, all we need to do is create our own root certificate and install it on any machines we want, and they'll blindly trust any certificates we signed. Yes, we have the power to do this. But before we go any further, I need to give you the great power, great responsibility talk. We're screwing with a chain of trust for your development machines. Don't do this if you're not confident in taking care of your private keys. If you do something stupid and put your private keys on, say, a public GitHub repo, someone could take that and forge certificates for any site your QA machines would connect to. Imagine what would happen if someone could eavesdrop on all your Slack chats. Basically, you're inviting a man-in-the-middle attack if you don't take care of your root private keys. I can't stress this enough. We're hijacking the chain of trust don't go into this lightly. Also, one disclaimer. If you screw this up and get compromised, it's your own damn fault. I'm not responsible for anything. So if you do get it right, you'll be able to test and deploy e-commerce sites with full confidence that they work well when encrypted. With all that over, let's look into the wonderful world of the openssl command. On this CentOS machine, I'm just going to replicate my setup. I have a single directory in my root folder called CA with some tight permissions. From here, I create 4 folders to hold the various files we need. One thing you'll need is my openssl config template. You can grab that from my GitHub, and I'll show you what each section does here and where we make changes. The first section basically declares that we are a certificate authority, and after that it goes into where the certificate authority files are located. We also establish the use of SHA-256 instead of SHA-1. You guys know why this is important. We also set up some defaults and loose trust policy. Remember, we're using this for encryption, not authenticity. So we're not going to bug the user for any information other than the domain name, which is referred to as the common name here. And that's all the setup information for a certificate authority that we need. Next, we're going to look at the configuration for the REQ section, which governs how the certificate signing requests are handled. Default bits is 2048, and that's okay as it is. Distinguished name is a subsection that we'll take a look at a little bit later. And specifying UTF-8 is a good thing, and again we're defaulting to SHA-256. V3 is another subsection we'll get into soon. So root distinguished name pretty much sets up the identification for the server. Since we don't care about most of this, I've just commented them out. And these questions and defaults may look familiar to you. The important thing is that we're capturing a domain name or common name. On to V3. So we're using the V3 format of the x.509 extensions. I know it's a lot of numbers and it gets a bit deep, but let's see if we could do this quickly. I'm literally summarizing the man page here. Subject key identifier basically means we're using the hash of the public key to generate the subject key identifier. Don't change this. Authority key identifier basically says use the key ID defined from the subject key identifier always, and if that doesn't exist, use the issuers. Basic constraints. So CA true means we're creating a certificate authority. Beyond this section, we're not going to cover anything today because sadly today's episode is a little bit longer than I would have liked. And I'm going to have to split it in two and leave revocation lists and a couple other things for next week. Those are mostly used for mitigation, so we don't need them this week. Now we have everything set up, let's start signing certificates. First, we generate the keys to our kingdom. So we tell openssl to generate an RSA key using AES-256 and write it to the file private/ca.key.pem, and also to use 4096 bits. In our directory, we chmod 400 to make sure no one else can mess with it. Next, we're going to generate a root certificate, which we'll distribute to our QA machines. This command is a little bit longer, partly because we need to specify the config file anytime we use the rec command. This may look very familiar, almost like that self-signed certificate we saw 5 minutes ago. And that's because all root certificates are actually self-signed certificates. So we generate a self-signed certificate using tag x509 for 10 years and specifying our v3 extensions and export it to ca.cert.pem. This is a file which we now can publicly distribute and install on our developers' machines. It'll show up later on the desktop of a developer's computer, and how it gets there is up to you, email, USB, whatnot. In the meantime, we're going to go through the motions and use our newly created root certificate and certificate authority to sign a server's website certificate. I'm going to switch over to the server right now, and I changed the prompt to blue so you know the difference between the machines I'm using. So on the server, I create a private key. Nothing new here. Instead of generating a certificate like we did for self-signed certificates, the next step is to generate a certificate signing request. This file will encrypt all of our server's identity. Since we're using a loose trust policy, we just need the domain to be right, and we have our .csr file. The CSR is sent to the certificate authority, so we're going to switch back to our certificate authority VM now, where we do a quick double check of the CSR. This command basically gives me a readout, and I can verify that the CN our common name of the domain is the one we want to sign. This all checks out, so now I'm going to run a batch command to sign the certificate, and we're using the config file openssl.cnf like usual. This is going to do its magic thing and generate a signed certificate for that URL. We grab the certificate and send it back to the server. I'm going to skip over the part where you get the website certificate and install it on the server. That process varies for each type of web server. Instead, I'm going to jump directly to the Keyway's machine and load the site using HTTPS. Firefox complains that it cannot trust the server certificate because it has no idea about the certificate authority that signed it. This is because we haven't installed the root certificate on the QA machine yet. Remember that self-signed root certificate that we generated? I've got it here on the desktop, and with this file, Firefox will blindly trust any certificate that is signed using our certificate authority. To install it, I'm just going to jump to Options, Advanced, Certificates, and import our root certificate. That's it, we're done. Now, if we reload the page, Firefox will happily accept the encryption for this domain. I'm going to drill down here and take a look at all the details of our very own certificate authority. Using this method, we could sign all the domains that we're working on, and our entire QA team can test development using HTTPS, just like how it will be in production. Okay, there you go, guys. I'm going to stop for today because it's been a little bit intense, and I hope some of you actually made it to the end. But I wouldn't suggest that you implement this right away. As I said, this episode ran longer than I imagined, and next week I want to cover certificate revocation lists and OSCP, so you can disable certificates that you no longer need. Until then, take care, guys, and I'll talk to you all next week.